Welcome to this second part of the open courseways dedicated to the hydrometallurgy of nickel ores. This part will be more dedicated to the presentation of a flow sheet of different processes, and you will see that. I remind you this diagram with different ore coming from the ore body of lateritic nickel. And with different processes, iron nickel smelting, HPAL high pressure acid leaching, ANS HPAL with high ratio of limonite on saprolite, and acid leaching with low ratio of limonite on saprolite. And I will describe you these different processes. The first one is what we call RKEF, rotary electric furnace processes. It's a processes used by ERAMET in New Caledonia. It's divided in different parts. First, homogenization of the ore, then drying of the ore to eliminate the water that is contained in the ore. You have a first pyrometallurgical treatment in a rotary furnace to reduce part of the ore, reduce the iron and the nickel, and then the smelting in the electric furnace. You have here the electrodes, and by smelting and reduction of the ore, you create two different products. The main product is that the ferronickel alloy, it's a raw material, and the magnesium content in the ore, the silica content in the ore goes in slag. That's a byproduct of this melting. On this ferronickel alloy, there is some refinery of this alloy and granulation, and you will produce such nickel small parts by granulation. You see that it's granulation in water, and you create this small shot of nickel. Another part of the ferronickel alloy could be treated with sulfur to produce a matte nickel sulfide. The second processes is the Caron processes, and that's the flow sheet of the Yabulu plant in Australia. You have the pyrometallurgical part. I remind you this process two parts, pyrometallurgic and hydrometallurgical part. For pyrometallurgy, you have the drying of the ore in a tube, then grinding of the ore and treatment in a vertical furnaces with introduction of reducing gas in order to reduce iron and nickel content in the ore in metallic iron and metallic nickel. The main thing is the leaching, the dissolution of the nickel with ammonia medium, and the characteristic of ammonia is that you can leach easily the nickel but not the iron, and the iron remains in the residue. You separate the residue with such device, that's countercurrent decantation, and the residue you treat it to recover some ammonia content, and you put it in a tailing disposal. On the solution, on what we call the leach solution, you have a solvent extraction of nickel to separate nickel from the cobalt. Then the solution containing the nickel goes in a stripping area to recycle the ammonia, and you precipitate then nickel carbonate. You calcine the carbonate to transform the nickel in nickel oxide, and you reduce this nickel oxide in metallic nickel, and you press it and you produce such nickel blocks. That's a production coming from Yabulu. For the cobalt, there is a cobalt sulfide precipitation, and then a refinery to eliminate all the impurities contained in this main flux. And you precipitate at the end a cobalt hydroxide. That's the product of Yabulu. But that was not the main part of my subject. The main part is acid sulfuric leaching, and all the processes I will present you have two different parts. The first part, we call that the front-end plant, and this front-end plant, the main driver is the quality of the ore. What you will have to put in the process, either limonite, either saprolite, or a mixture of limonite and saprolite. The second part of the plant is the solution. By leaching, you produce a solution containing nickel, cobalt, and impurities, and you would have different kinds of processes to treat this solution, to separate the impurities, and to recover nickel and cobalt, either in a same product or dissociated, a nickel product and a cobalt product. For the front-end plant, different part. The first part is the leaching. You dissolve the ore in the acid. You precipitate the iron. You have acidic condition in order to precipitate the iron. You neutralize the remaining acidity by limestone, and you have a separation of the residue, iron residue, from the solution. The main thing is to recover the solution and to recover all the nickel content in the solution. And then, as I already have said, purification of solution and recovery of nickel and cobalt. Now, some real chemical words. You have to know that the ore you treat, it's mainly iron ore with very high content of iron. But iron has no value, and you have to put it in a residue. And you have to know how to process this iron. And the main driver of such processes is how to manage the iron. You see here a diagram. It's stability of different iron species according to the pH of the solution and to the temperature of the solution. At high acidity, you dissolve the iron as iron 3. That's the reaction I put here. You leach the goethite, the iron oxide, with sulfuric acid to create soluble iron sulfate. After that, depending on the parameters, operating parameters, if you stay at rather low pH, high acidity, and if you have some sodium in the solution, sodium is coming from seawater, you precipitate iron as jarosite. Jarosite is a mixed sodium iron sulfate. If you increase the pH, decrease the acidity, three different kinds of iron minerals. At a rather low temperature, you precipitate iron oxide. At 80 degrees, you precipitate goethite, and at high temperature, you precipitate hematite, iron oxide. Why this kind of diagram is very important? Because at high acidity or high pressure, the conditions, the parameters of leaching are very drastic, and it's a way to well dissolve all the solution, all the nickel, and to get very high yield of nickel recovery in the solution. As at rather smooth parameter operation, you precipitate the goethite, but you will decrease the iron recovery of such processes, and you will see the results in the presentation. Another thing, also very important, it's chemistry. I remind you have dissolved the iron, and in the same area, in the same vessel, you will reprecipitate the iron as hematite, goethite, or jarosite. When you reprecipitate the iron, you see this reaction, you create acidity. That's the main thing for goethite and the main thing for jarosite. You see the H+, that's the acidity created during the reprecipitation of the iron. And with different acid regeneration ratio depending of the minerals you have precipitated. For hematite goethite, you recover 3 H+ by iron, and for jarosite, you recover only 2 H+ for 1 iron. And this acidity formed during reprecipitation will be used for the dissolution of the iron. It's a continuous operation, dissolution by acid, reprecipitation of iron, and then you form back an acid that is used for the leaching. The conclusion of this acid ratio is that when you precipitate hematite and goethite, you will form more acid and you will consume less acid than for jarosite. You form only 2 acid per iron, and the conclusion is that the acid consumption will be higher than in the other processes. Now I will enter in details of the different processes. The first one is the HPEL simplified flow sheet. You have here the autoclave at 40 bars or up to 50 bars, 250 degrees. You put it the sulfuric acid and the limonite. You dissolve the limonite, and in this autoclave you reprecipitate the iron as iron oxide. You see that dissolution of the goethite, formation of ferric sulfate, and reprecipitation of the ferric sulfate in hematite. The nickel is also dissolved by this equation, and you form a specific metal bisulfate of nickel. After this dissolution, you separate the sulfate solution, the nickel cobalt sulfate solution, from the residue by what we call a countercurrent decantation. It's a way to wash the residue and to recover all the impregnant solution from the residue to have a very high nickel cobalt recovery in the leach solution. The main advantage of such processes is that there is a very low level of acid consumption. You will see the figure after the different presentation. But there are some drawback of such processes. You see 250 degrees C, 40 bars is very high pressure, and it's very expensive equipment, a very high capex, and a technology, some risk of the technology, some risk of pressure leakage, and so on. It's very difficult to manage such device. The other drawback is that there is a limitation in magnesium content due to the fact that during the leaching of the magnesium oxide, you create what we call bisulfate of magnesium, and this bisulfate consumes large quantity of acid. That's one of the drawbacks. The other drawback is that with magnesium, aluminum, and chromium, and mainly with the magnesium, you form some crust and scales inside the autoclave, and you decrease the volume of the autoclave by formation of this crust. And you have to stop very regularly the autoclave to clean it. The conclusion is that for such device, you can treat mainly limonite, 80% of limonite, but you are limited in saprolite treatment in the level of 10%. 3 examples of such processes. It's rather complicated. It's the marine flow sheet in Australia. What you can see here is that autoclave, 4 autoclaves in series. That's a picture of the autoclaves. It's a very huge equipment. You see here the CCD, the countercurrent decantation, to separate the residue, and you have a treatment of the residue, and you put the residue in a dam, in a tanning dam, and separation of the liquid. On this liquid with nickel content, you have first precipitation, neutralization of the solution, and you add some hydrogen sulfide here to precipitate nickel as nickel sulfide. It's an intermediate product. The choice of this process is to have a solid intermediate product, mixed nickel cobalt copper, zinc, iron sulfide, and to let in solution other impurities, aluminium, chromium, manganese, and magnesium that are put in the residue and put in the tailing. That's the first part of this flow sheet, the front-end plant. And on the nickel sulfide, you can either sell it, or you can treat it, redissolve the nickel in an autoclave, purify the solution, and recover the nickel by hydrogen reduction in other autoclave and producing nickel pellets. And that's nickel pellets coming from marine. That's the same thing for the cobalt, reduction of the cobalt in a specific autoclave by hydrogen and production of cobalt pellets. Another type of processes on HPEL flow sheet, it's Ramu in Papua New Guinea. You find here the preparation of the ore, treatment in the HPEL, in the autoclave. It's a rather simple flow sheet. Then neutralization of the slurry coming from the HPEL to neutralize the acidity, the CCD, countercurrent decantation, to separate the residue and to treat the residue, and to recover a solution with impurity removal, impurities as chromium, aluminium, and iron, and then precipitation of nickel cobalt, precipitation with caustic soda, and production of what we call a MHP, a mixed hydroxide product. And you find that this green, yellow-green products, that's MHP. And you see in this process, they stop at this intermediate product, and they sell this intermediate product. It's a mixed nickel cobalt hydroxide. That beautiful picture of the Ramu plant. You find here preparation acid plant to form the acid needed for the processes. Here you have 3 autoclaves. You have the countercurrent decantation, the residue treatment here, and then precipitation, neutralization of the solution, and precipitation of the mixed nickel cobalt hydroxide. The last process I want to show you for the HPEL flow sheet, that's the process used in Goro in New Caledonia. In this process you have the feed preparation with limonite. We see they say that they could have up to 15% of saprolite. It's rather high content. Pressure acid leaching in autoclave, countercurrent decantation, solution purification to purify to recover the cobalt, and a specific process developed by Goro Nickel. It's a direct solvent extraction to recover nickel and cobalt from this solution. And after this recovery, in the solution remains only the manganese and the magnesium, and they are neutralized and put in a residue. On the stripping part, on the element coming from the solvent extraction, they recover the zinc on ion exchange resin, and there is a second solvent extraction to separate nickel and cobalt. On nickel, they have some pyrohydrolysis of nickel to produce nickel oxide, and for the cobalt, they precipitate the cobalt as cobalt carbonate. You see the front end is rather identical from the other HPEL process, but the solution treatment is completely different and is depending of the product you want to sell and to produce. Another flow sheet, the EHPEL, hence high pressure acid leaching. The flow sheet was used at Ravensthorpe in Australia with 2 parts. First, the classical one with the autoclave, dissolution of the limonite with sulfuric acid. And on the slurry coming out from this part, this high pressure acid leaching, you have a second reaction where you put saprolite and you use excellentary acid coming from the nickel bisulfate to leach the saprolite and to dissolve the magnesium silicate in order to liberate the nickel content in this silicate. Two parts, high pressure and atmospheric pressure acid leaching. Depending of the water used during these two parts, either fresh water or seawater. Here you will precipitate, I remind you, with fresh water you precipitate goethite, or with seawater you precipitate jarosite. The advantage of this flow sheet is that the acid consumption is rather low, and you can increase the ratio of saprolite and limonite. You see you are at the level of 70% of limonite and 30% of saprolite. But there remains some risk on this part of the acid, high pressure acid leaching, risk on technology and very high capex for these processes. Here you have the detailed flow sheet of Ravensthorpe with here the pressure acid leaching on the limonite, the atmospheric leaching on saprolite, after that neutralization of the solution, separation of the residue on countercurrent decantation, treatment of the solution in different parts, precipitation of impurity with limestone addition, precipitation of MHP, mixed hydroxide produced with magnesium oxide, in order to produce the same product, I said you mixed hydroxide product, and then you have a final recovery of nickel, recycling of some nickel in the beginning of the process, and a specific manganese removal part due to the fact that there is a certain quantity of manganese in the ore. Some pictures of Ravensthorpe, the acid plant to produce the acid inside the plant. The HPAL process, we don't see the autoclave is somewhere there. Then the atmospheric leaching is done in these reactors in series, and the countercurrent decantation in this very huge CCD. The other type of processes, atmospheric leaching, complete atmospheric leaching. This processes was developed by BHP with, you see, it's divided in two parts. In the first part, at atmospheric pressure, you dissolve limonite with sulfuric acid and you put all the iron in solution as iron 3 sulfate. You dissolve also the nickel, and you decrease the acidity, you increase the pH by adding saprolite, and by adding saprolite you create condition where you can reprecipitate the iron as goethite if you use fresh water, or as jarosite if you use seawater. And after that you have neutralization. The advantage of such processes is that that's very simple reactors, equipment. You decrease the capex of the equipment, and it's a very well-known technology used all over the world. You can increase the saprolite treatment. You see the ratio, 50% of limonite, 50% of saprolite, and the saprolite treatment could be separated. The drawback is that you increase the acid consumption. The last process is the process used by ERAMET. The main difference towards the other processes is that you do all the reaction in the same vessel, in the same reactor. You put limonite, you put saprolite, you put seawater, and in the same reactor, during the same time, you dissolve the goethite in iron sulfate, you dissolve the nickel content in the goethite, you dissolve also the magnesium silicate coming from the saprolite, and you dissolve also the nickel content in this magnesium silicate, and in the same time, in the same vessel, due to specific parameters, you reprecipitate the iron as jarosite. And you do that in only one step. The main advantages, you decrease the capex when comparing to HPL. It's a very well-known technology. And another advantage is that you treat both limonite and saprolite, and you don't have to separate it on the mine. You can have a mixed ore treatment, and that's a very huge advantages when you have a high quantity of what we call earthy saprolite. It's a mixture on the mine of saprolite and of limonite. The acid consumption is rather high, but the energy consumption is rather low. With all this information, you draw these tables where you compare the different processes, HPL, hence HPL with precipitation of iron as goethite or of precipitation of iron as jarosite, the atmospheric processes with goethite iron acid leaching, jarosite acid leaching, and the ERAMET processes. Depending on this process, you see the ratio of limonite on saprolite you can treat in the process, and you can increase the saprolite content in this atmospheric leaching process. Process water is also different, and it's very important because in some part of the world you don't have access to fresh water. You are near the sea, and you have a lot of seawater, and it's very important. It's easy to use the seawater and not easy to use fresh water. That's the fact in New Caledonia, also in Indonesia, where there is a lot of seawater, but also in the Australian desert. In the Australian desert, you don't have fresh water. You have also salt water as seawater. Nickel leaching yield, you can see there is some differences. For this very high pressure acid leaching, nickel recovery could be higher than 95% recovery. When you mix the high pressure acid leaching with acid leaching, you decrease the nickel yield to the level of 90%. If you use goethite acid leaching at low pressure, you see you decrease at the level of 85% the nickel yield. But when you precipitate iron as jarosite, it's at higher acidity, you increase the nickel recovery yield, leaching yield at the level of 95%. Iron residue, quite different, hematite, goethite or jarosite, depending on the processes. Technology risk, very high for HPAL due to the fact that you use very high pressure acid leaching, and this risk decrease when you are with atmospheric leaching processes. Acid consumption, that's very important because in such processes the cost is mainly due to the reagent consumption and the acid consumption. For HPAL, you are at the level of 0.3 to 0.4 tons of acid per ton of ore, and going to these processes at atmospheric pressure, you are at the level of 0.7 to 0.9 ton of acid per ton of ore. It's a real drawback, but there is a main advantage to have this very high quantity of acid due to the fact that the acid is produced on place by treating sulfur. There is a lot of sulfur available in the world, and when you burn the sulfur to create acid, you create energy, and you can recover this energy. And you see, when you recover this energy, you have all the energy needed for the process, to heat the equipment, to have electricity for the pumps, for the stirrer, and so on. And you see that for limonite, the fossil energy consumption is rather high. For a plant at the level of 60,000 tons of nickel, energy consumption is 67 megawatt. As when you go at atmospheric processes, you decrease the energy consumption due to the fact that you recover energy from the acid production, and you are at a level of less than 5 megawatt. Another consequences of this energy consumption is the gas emission. You see, we have calculated the CO2 created by this process, and it's at a level of 50 tons of CO2 per ton of nickel. And when you decrease the fossil energy consumption, you decrease the CO2 formation, CO2 creation, and you could be at a level of only 4 tons of CO2 per ton of nickel. Okay, that's the end of the second part of the courseware. Thank you very much. I will wait you for the third part of the courseware.